Are we the only intelligent life in the universe? This is probably the oldest question in the history of mankind. And while science fiction writers, UFO enthusiasts, and religions the world over certainly have their own answers to this question, the scientific community at large has still not found an answer they would consider definitive, despite the best efforts of programs such as that of the SETI Institute. And in this video, we're going to explore why. That question lies at the heart of a very famous problem called the Fermi Paradox, which goes something like this. The likelihood of intelligent life out there in the cosmos beyond Earth is high, given the age of the universe, the size of the universe, and the number of planets in the universe. So why have we detected no sign of it whatsoever? A lot of different solutions to the paradox have been offered over the years, and I'm going to go over all of those. And then I'm going to tell you what I think the real solution is, because I believe that they are overcomplicating the issue. So, let's go inside of my computer and get to it. The complete list of Fermi Paradox solutions is too numerous to cover in one video, but here are 6 of the most popular, and then I'll tell you what I think the real problem is, and how I think we can solve it and detect extraterrestrial signals. The first is called the zoo hypothesis. This is the idea that aliens are operating on a principle similar to the Prime Directive in Star Trek. Don't interfere. The second is that we are living in a simulation. Now, this is obvious what that means, and they're basically implying that it's not repeated over and over and over again because of computer resources. The third, aliens are broadcasting, but we don't know how to listen. Now, SETI, the Search for Extraterrestrial Intelligence, is counting on this solution. And this is the idea that the aliens are broadcasting, but they're using some technique that we don't know how to pick up. 4 is the rare Earth hypothesis, which supposes that our planet is rare in the universe, that it is not as common as we might think it is with our type of star and the conditions on our planet. Number 5 is the youngness paradox, which is just a fancy way of saying that our universe is not old enough to have more than one of our type of civilization. And the 6th one is probably the most well known. This is called the Great Filter. And this is the idea that the development of a civilization that can colonize the galaxy is a unique and maybe once in a universe event because of the many exceptional barriers to life along the way. So, what do I think is really going on? Let's talk about that now. I'm under no illusions that anybody's going to be handing me a Nobel Prize for stating the obvious here, but while those solutions are definitely interesting and thought-provoking, they're also highly speculative and, as I said at the start of this video, overcomplicated. I think that the real truth about why we haven't detected any extraterrestrial signals yet can be boiled down to a combination of 3 factors. 1, failure to take into account how all light, including radio waves, behaves over vast distances. 2, failure to take into account the signal strength necessary for transmission to have in order for it to be detective of the background noise of a civilization's parent star. And 3, faulty assumptions on the parts of the people doing the searching about the civilizations they're searching for. And frankly, I'm a little shocked by this myself, given that these are not only extremely intelligent people who are highly respected in their fields, but the first 2 factors in that above list are things that other astronomers and physicists deal with on a daily basis, particularly those running exoplanet hunting missions like Kepler, TESS, and their ilk. The first 2 items in my list work hand in hand to form the pure science half of my equation for solving the Fermi Paradox. So I want to start there. We can't see radio waves after all, but a photon is a photon and they all play by the same rules regardless of frequency. As light travels further and further away from its source towards an observer, two things happen. The first thing is that it diffuses or spreads out, causing it to become blurry and distorted to the observer. That's why Mars looks like the image on the left to an Earth-based telescope and the image to the right to a much closer Mars orbiter. The other thing is that light gets less intense and therefore dimmer the further it travels, thanks to something called the inverse square law. I won't bore you with the math, but this is one of the ways astronomers can determine how far away something is. The greater the distance between the source and the observer, the more pronounced both effects become. If you've ever tried to tune into your favorite FM radio station while driving out in the middle of nowhere and gotten static, you've experienced both of these effects firsthand. That's because the signal is still there, but by the time it gets to you, it's so weak and distorted that you can't distinguish it from the background noise. And that's just over a distance of a few miles. Now try multiplying that by several billion, or trillion rather, to light years, and you begin to see why we might have a problem detecting extraterrestrial signals. That's just the start of the problems for programs like SETI, though, because this is where the second item in my list comes into play. See, that weak and garbled signal might still be detected by our technology, even among all the radio waves and dust clouds it has to go through on its way to us that intensify those effects. But there's an even bigger problem that's a lot harder to deal with. That civilization and their transmitter are parked around a star that's putting out massive amounts of radio interference with all the same intensity that it puts out visible light. Returning to our car analogy, if you've ever been on the interstate with the sun shining directly in your eyes and tried to see a car several miles ahead of you, you know why this is an issue. There are two ways for a civilization to overcome all these technical difficulties, but both are impractical and highly unlikely. They can either broadcast from a location much closer to us or any other civilization they're trying to talk to, or they can broadcast the signal with more intensity than their star produces. One way would require them to travel so far out they might as well visit another civilization in person, and the other would likely wipe them out in the attempt. Is it any wonder then why all we've detected in our years of listening is natural phenomenon and false alarms from near-Earth technology? Now, let's talk about the common sense part of the equation. Common sense half of the equation is where the third item in my list comes in. That's because while the SETI Institute, along with its predecessors and international equivalents, have made a lot of good science-based logical assumptions about extraterrestrial civilizations and how they might reach out, they've also made assumptions that I've always found questionable at best because they're based on conflicting ideas. On the one hand, that they are thinking like us in terms of the best kind of signal to send out, and on the other, that they are not thinking like us in terms of methodology and mindset. The assumption that's always bothered me most personally is that they are transmitting rather than listening as we are. And that's because that idea brings with it a whole host of problems that make it seem rather unlikely that anybody out there is sending deliberate signals. Just to name two. One, it is doubtful that any civilization out there is going to be transmitting a signal unless and until they are absolutely sure there's somebody out there to talk to. And two, this means that they would have to have already detected us, which in itself is a problem in terms of time and technology. The only signals we've really sent out in amounts big enough to grab attention are our radio and TV signals. One major problem with that is that since radio waves travel at the speed of light, and we've only had that technology for about a century or so, that severely limits the number of stars our signals have reached. The other is that those signals are significantly weaker than the signals we'd expect to be receiving from them, and they're subject to the same problems that we've already discussed in the last segment. Just as an alien civilization would have to either transmit from so close they might as well visit, or else have to transmit a dangerously powerful signal to overcome those problems, they'd also either have to either be that close or else have an absolutely huge receiver in order to detect our signals. Which means in the former case that you'd better damn well be ready and willing to accept UAPs or UFOs as a legitimate scientific possibility, and in the latter make some further assumptions about the priorities of that society, because it would take time, resources, and society-wide cooperation to do it. We haven't built a receiver capable of receiving their radio and TV signals yet for those very reasons. Why then is it logical to assume they have? That's just scratching the surface of what, to me, are faulty assumptions on the part of SETI and its kin. And none of that is even to mention that if either of the above scenarios were true, we'd have observed some kind of evidence to that effect. And maybe we have, but science just isn't ready to take it seriously yet. All that said, I think there's still hope that we can detect extraterrestrial signals and finally put the Fermi Paradox to bed once and for all. So now let's talk about some ways I think we can use to improve our chances. There's a principle called Occam's razor that states that with any given problem, the simplest solution is usually the right one. Now, I think that if we apply Occam's razor to the Fermi Paradox and add together those scientific and common sense variables we just finished discussing, then we can come to the conclusion that the reason we have not detected any alien signals yet is because they're listening, but they simply have not transmitted a response. And that would either be because they have not detected our signals yet, or else they have detected our signals and have chosen not to respond for the simple reason that they are smart enough to realize that sending a signal powerful enough for us to be able to detect across light years of space would require so much energy that they would probably destroy themselves in the attempt. That said, I do think there are some things that we can try that might, and I want to emphasize that word, might work in increasing our chances of detecting those signals. Now, the first one is to not focus on powerful signals being beamed directly at us, but to focus on radio and TV signals. Now, I know that may sound like I am contradicting myself because of what I just said about needing a huge telescope to be able to detect radio and TV signals across space, and in most cases that might be true, but there is a huge caveat that might give us a fighting chance in detecting radio and TV signals from another civilization. There is an algorithm that's been developed to reconstruct signals that have been degraded from being diffused and their signal strength weakened by traveling across space. If we're able to develop some kind of AI that's sensitive enough to be able to pick out such weakened signals and separate them from the background of space, and we combine them with that algorithm, we might have a chance at reconstructing that signal. Now, I think that we deserve to try it ourselves, because before we go assuming that another civilization has picked up our signals and is sending us a response, we need to even see if it is possible to receive those kind of signals from across great distances like that. Now, the second thing is to use a couple of tools that are already in astronomers' toolboxes, just use them in a different way that might help us to detect some technosignatures.
Now, there have been some attempts at detecting the technosignatures, but not what I am about to suggest. Now, the two tools that I have in mind are transit spectroscopy and radio spectroscopy. Transit spectroscopy is what the astronomers use to analyze the atmospheres of planets that orbit other stars when they pass in front of their sun. The visible light passes through, they divide it up into a spectrum, and since different chemicals absorb specific wavelengths of light, whatever's missing from that rainbow tells you what's in the planet's atmosphere. Now, if we can use that to look for things that should not be in a planet's atmosphere unless there is civilization there, such as industrial pollution, pollutants, and isotopes that would only appear in a planet's atmosphere once nuclear testing has been started on a planet, that would be a technosignature. And as far as radio spectroscopy, which is the science of analyzing the radio signals that are emitted and absorbed by objects, we might be able, if we can use that the same way that we use the visual light spectroscopy for transits, we could actually use the stars, the parent star's background noise, to our advantage. Because if it works the same way and different materials absorb and emit, in different ways, then we can use that to detect things that should not be there unless there is a technological civilization, such as synthetic materials and natural materials like glass and aluminum and plastic. Now, these things we wouldn't be able to detect on the planet's surface. That's impossible. But from the vast distances we're talking about, things like, if they're a space-faring civilization, chances are they've got space junk orbiting their planet, just like we do. And that space junk would appear to be part of the atmosphere from this distance. So, if you're using radio spectroscopy and you detect aluminum or titanium or glass or plastic or something like that, and what should be the planet's atmosphere, that is a definite technosignature. Now, like I said, I don't know if these things are possible, but I'd like to know what you think. What do you think about the Fermi Paradox and my solution for it? Let me know in the comments. And also, don't forget to like this video and share this video and subscribe to this channel because it really helps me out. Alright guys, that's it for this video. I will see you for the next one. Until next time guys, peace.